Everyone, in this video I shall be discussing the physics problem of vertical circular motion of a particle with quadratic air resistance. First, read out the problem statement. A particle is imparted a horizontal velocity u at the bottommost position of a smooth vertical semicircular track of radius r. Air resistance is active as per the quadratic law. F vector air drag equals to negative k times square of v vector magnitude multiplied by v cap. Find the minimum value of u required for completion of the vertical circle. The figure corresponding to the problem is shown. One thing I'd like to mention before proceeding is about the expression of the air resistance force here. This expression means that the air resistance force acting and on the particle at any moment is proportional to the square of its speed at that moment. The proportionality constant being k, it's a positive constant, and this force is directed opposite to the particle's current velocity vector, that is opposite to the direction of motion. Start with the solution. First of all, the track is circular and the particle moves over it, so it will obviously perform circular motion. And in circular motion, we work in terms of radial and tangential directions. So as a first step, we have to draw the free body diagram of the particle at a general position. Now, what's the general position? The general position in circular motion is a position up to which the particle has covered an angle theta, starting from when it began moving, and it has covered a circumferential distance, that is, distance along the periphery of the track equals to small s. At this moment, it has a velocity vector with magnitude v, that is, its speed is v, and it has arrived at this general position in a time small t. At this position, we have to identify various force vectors acting on the particle and represent them pictorially. This pictorial representation will be called the free body diagram, or the FBD. In our case, three forces act on the particle at the general position. They are shown. They are the normal reaction from the surface, the particle's weight, and the quadratic law, and the air resistance force following the quadratic law. Next step is to apply the Newton's second law of motion on the particle at this moment. For a particle, Newton's second law states net F vector net equals to m into a vector. That is, the net force vector on a particle at any moment is equal to the product of its mass and its acceleration vector at that instant. This is a vector equation. We Before applying it, we need to resolve it into component form. In circular motion, we resolve our forces into radial and tangential directions. So the Newton's second law, therefore, written on top, can be broken down into two separate equations. Along the radial direction, we have Fr net is m into ar, the net radial force is mass times radial acceleration. Along the tangential direction, Ft net is m into at, the net tangential force is mass into tangential acceleration. Along the radial direction, the forces acting toward the center will be taken as positive, and those opposite to it will be negative. Also, by definition, the radial acceleration of the particle at a moment when its speed is v equals to v squared upon r. Along the tangential direction, the forces acting along that tangent, which is parallel to the particle's velocity vector, will be taken as positive and those opposite to it as negative. Also, the tangential acceleration at by definition is the rate of change of particle speed dv by dt. So in our case, Newton's second law gives us two equations, two force equations along radial and tangential directions. They are n minus mg cos theta is mv square over r, and minus mg sin theta minus kv square is m times dv over dt. The next step is to solve these equations. Let me write them down once again. We have n minus mg sin theta mv square by r and minus mg sin theta minus kv square m times dv over dt. There is an alternative expression for tangential acceleration other than dv by dt, which is useful sometimes, and it will be useful even here because time is not appearing in either of the equations. Instead, the space coordinate theta is. So dv by dt can be written as v dv over ds. What is s here? As I told previously, this is the initial position. This is the general position. And from initial to general position, the particle has covered an angle theta, a peripheral distance s. Right now its speed is v. So how do I arrive at this expression? I take this expression dv upon dt, multiply and divide it by ds. Multiplying and dividing by the same quantity doesn't affect it. Then I interchange the denominators of the fractions, dv by ds here and dt below ds here. ds by dt is by definition v, v dv by ds. Also, in circular motion, the arc length is related to this angle subtended by the arc at the center as s is r into theta. If I take differentials on both sides, I get ds equal to d of r theta. R is a constant, it factors out, so it is r times d theta. So in place of ds, I can write r times d theta. So what I'm going to do is I'm going to write tangential acceleration dv by dt as per this expression. That will be needed if I have to solve this. V dv over r d theta. So I am write this as m times v dv over r d theta. So we have two equations and we have two unknowns. One is v as a function of theta and second is n as a function of theta. We have to solve for two functions. Now clearly the second of the equations does not contain the other variable n. So we can solve v as a function of theta from equation 2 here. Once we obtain it, we'll feed it here in the first one and then we'll get n as a function of theta as well. So for now we focus our attention on the tangential force equation. We can write it down as v dv over d theta is negative rg sine theta minus kr upon m v square. Introduce a change of variable. Let v square equals to another variable p. Taking differentials, we get d of v square is a differential change in p, and by chain rule d of v square is 2v times dv. Therefore v dv is dp over 2. So this implies dp over 2 d theta minus rg sine theta minus kr upon m times p. This implies dp over d theta is 2 kr upon m times p minus 2rg sine theta. This equation that we have arrived at here is a first order linear ordinary differential equation. It is a standard differential equation which has a standard solution arrived at using the integrating factor method. I'll write down its standard form and the solution corresponding to it without going into details of how that solution is derived. And then we'll use that solution in our particular problem. So dy over dx plus y times p of x equals to q of x. Px and qx are functions of x, the independent variable. This is a standard first order linear ODE and its solution is given by general solution y into if is integral of the product of functions qx and if plus c, c being an arbitrary integration constant, and if the integrating factor is given by e to the power integral px dx. Comparing with our equation, in our case the integrating factor is e to the power integral 2kr upon m respect to theta. This is 2 e to the power 2kr upon m integral d theta equal to e to the power 2kr theta over m. Therefore, our general solution will become p times e to the power 2kr theta over m equals to integral minus 2rg sine theta multiplied by e to the power 2kr theta over m with respect to theta plus c. And since negative 2rg is a constant, it can be factored out. I can write this as minus 2rg times this integral here is a standard. It can be evolved using the technique known as integration by parts. You can look about the details of that technique in any any calculus textbook. I won't be going into its details. I'll simply write down the integral evolved after applying the technique. P was by definition v square, so here we have v square times e to the power kr theta over m negative 2rg. And now this integral, it is e to the power 2kr theta divided by m multiplied by square bracket 2kr upon m times sin theta minus sin theta divided by 1 plus 2kr upon m whole square plus c. And if I multiply throughout by e to the power negative 2kr theta by m, I'll have an e to the power negative 2kr theta upon m here. And here I'll this term will be reduced to 1. So I'll just write it down. The constant c here is an arbitrary integration constant, and it needs to be obtained using the initial condition. In our case, the initial condition is that when the motion began, that is when theta was 0, velocity imparted was u. Therefore, v at theta equal to 0 is equal to u. Therefore, we get u square is negative 2rg. Actually, 2rg, wait, 1 plus square of 2kr upon m plus c, yeah, plus c. This implies c is u square minus 2rg over 1 is 2kr upon m whole square. So I can write c here to complete my general solution. U square minus 2rg 1 plus 2kr upon m whole square complete multiplied by e to the power negative 2kr theta divided by m. So that completes my solution for v as a function of theta. The other variable I had was n as a function of theta. And if you recall the radial force equation, it was n minus mg cos theta is mv squared by r. So n is mg cos theta plus mv squared by r. So if I feed v, expression of v that I obtained here in the expression of n, I can then get an expression of n. It is n is equal to mg cos theta plus mv squared by r. So this can be m u squared upon r minus 2mg over 1 plus 2kr upon m whole square complete multiplied by e to the power negative 2kr theta over m minus 2mg divided by 1 plus square of 2kr upon m times 2kr upon m sin theta minus sin theta. So is this. So finally, we get an expression of v and n, and we are interested here in the expression of n, not v, because what we need to find is the minimum velocity of u required for completion of the vertical circle, and condition for the completion of vertical circle is that at the topmost position, normal reaction should be greater than or equal to 0. So we require n at theta equal to pi greater than or equal to 0. Let's apply it. Mg times cos pi is negative 1, so minus mg plus mu square upon r minus 2mg upon 1 plus kr upon m whole square times e to the power negative 2kr pi upon m minus that should be plus 2mg upon r upon m whole square. This must be greater than equal to 0. I can take this mg on the other side. Need some more reshuffling of terms. One more, one or two more steps maybe to arrive at the final expression we need. We get mu square upon r minus 2mg divided by 1 plus 2kr upon m whole square is greater than equal to mg minus 2mg over 1 plus 2kr upon m whole square times e to the power 2kr pi upon m. If I take this term there, 2mg upon this term, it will be 2mg over 1 plus 2kr upon m whole square. And now I'll simply divide both sides by r over m and then take square root. I'll then get my minimum value of u. So finally write down the expression sought to we were seeking. U greater than equal to rg minus 2rg upon 1 plus 2kr upon m whole square multiplied by e to the power 2kr pi over m plus 2rg upon 1 plus 2kr upon m whole square and square root of this entire thing. So u must be greater than equal to the right hand side. So the expression on the right hand side is the minimum value of u that we need for completion of the vertical circle. Hope this helps. Next time we'll see another unique physics problem. Thank you for now.